Yeah? Cool. So I'm Guy Arazi. Today I'm going to show you a research that I've conducted in Microsoft that essentially allowed me to uncover a novel technique that deals with SSRF exploitation in defense. And I will walk through everything that we do and how we've done it and what are the mitigations that we're proposing for SSRF, etc. So first of all, about me, I work in the Microsoft MSRC vulnerability and mitigation research team. We essentially take all the vulnerabilities in Microsoft, try to assess them, triage them, validate them, and propose the right mitigation that has the most impact on Microsoft across all of our products and features. I've been also in the EDR research team and other vulnerability research group like Azure, also former Palo Alto. I've been passionate about security, I think, most of my life, and it's something that was always bounded in me. I have a few other hobbies that are not security, which are like CrossFit, bonsai, and do other things that are not related. And let's start. So everyone knows what the SSRF is, right? We have some basic URL fetching endpoint that allows you to request a resource from the server endpoint. Now, it allows attackers and finders and like researchers access internal network resources by breaking parsers and accessing assets that they shouldn't. And like we think that we've seen everything. So we have so many payloads and utilities and tooling to leverage SSRF, and everything that think that they are already safe, right? We have the proper mitigation for SSRF, which can be application level in terms of like blocking known internal IPs, use proxy with URL rewriting from the external to try and avoid accessing all kind of internal paths or areas that we don't want the user to access. Also have some network segmentation capabilities that are mainly around the host or the VPC that blocks internal access to the sensitive host. And then lastly, we also have WAF rules that are blocking common payloads. So we all probably, most of us saw tons of GitHub repositories and other documentation that explicitly mention most of the SSRF primitives and how to break parser around many features and languages and interpreters. And like we all know them, like we can block IPs to internal resources, block maybe even scheme ports, or even go on the other side, try to whitelist specific subset of hosts and only allow accessing these type of assets. Now, looking at it from the perspective side, like the external perspective side, once I communicate with the service externally, I go through a pipeline of many features and products and applications that do all kind of different things along the way. So we start off with a firewall, and then we go to a load balancer and WAF, and each one of them like can strip headers, add headers, reroute and change the path that we're accessing to. Anything that you can imagine that goes through this pipeline is all about trying and keep the organization or the customer end protected from the outside, which is fine. And we all know things like WAF can block internal IP ranges, all kind of known payloads, restrict protocols, and in some cases, which is not mentioned here, but we can also whitelist common parameters or values within the WAF that will allow us to block SSRF essentially from this side of perspective. We also have IP tables, so these IP tables can block a specific interface card from accessing internal resources. But what about the loopback interface? The loopback interface essentially can access anything on the system because it's not coming from a perspective of an interface that sits on the LAN, it sits locally on the host. There are other things like proxy rewrite URLs. So if there are sensitive paths or sensitive locations that we don't want the user to access, we can straight up and rewrite the URL that they are trying to access and restrict them by either redirecting it to a different one or just blocking the endpoint. And it can look like something like that. We can also create an access rule on Nginx that essentially everyone that access internal deny them, but if they're coming from an internal asset or internal node, you can allow it. And this just shows us that things like that can be all along the way to the pipeline, and it's not just falling into one particular spot. And there is also an application level protection, which essentially, there are so many variations of that, right? Because we can, every developer and every team and every company implements their own mitigations for SSRF. Really depends on the implementation of what the service actually does. Now, in this case, we're taking the origin, which comes from the host header, and we're trying to check if the origin is actually something that comes from internally. And if it does, we can allow for this action to happen, because at the end of the day, there are other internal APIs that communicate the same ones externally, which they serve the same functionality, but because we want them to provide and communicate with service-to-service endpoints, we kind of bypass this mitigation in order to not create a different service for the same functionality. So if you didn't get it right, external doesn't mean trust. Like, we look in it in the sense of there are so many security security components like WAF rules, rewrite, URL rewrite, IP tables, origin check. And all these are being blocked from the outside perspective because they are only applied on the outside. They never speak about what happened inside. But what if the position matters more than the payload? Like, what about a vulnerability that works the same that it works from the outside might work differently from the inside? And we're just defending from different aspects of the wrong vectors, and we're relying on things that are more signature-based and not behavioral, or at least fundamentally speaking about the application security stack, and just about to defend against something that we already know. And the position matters more than we think. And the idea is to understand that if a primitive can be accessed from the outside, it might be accessed from the inside as well. And this is pretty common. I'm not trying to come up with something new, but SSRF², essentially what my research is about, is essentially gain an internal access position. So we have one primitive which is coming from the outside world, let's say some API endpoint, and the second primitive is the same one that points to the same API endpoint, but different security context. So when we access from external resource, we have some context of security. And when we gain for the same one, internally, we have a different security context and different trust boundaries. One second. So basically, this is how it looks. So we have an attacker or researcher, whatever you want to name it, accessing an external context. So we have this external host /fetch that gets a URL parameter. This URL parameter will be then fed into the same primitive that points to the local host, and then we can chain this up, because we're now in a different context, security context, we can chain it up with things that are blocked from the outside to the inside. So essentially, if this target server or essential API endpoint is blocked from the outside, we can chain the SSRF and run them twice in order to find targets that are blocked from the outside. Now, our goal is mainly, especially when we take down SSRF and try to break it down, it's very easy to just fuzz your way out with all the payloads and try to understand, like, maybe I can just run all the ports and understand what's going on in the network. But all along the way, there are things that exist on the application level, and the same one that you already exploited, that essentially allows you to gain more instead of doing more, because we already have some primitive that has more value than we think. And I'm going to also show you a few cases. So this CV was rated for 8.8. It's a service, a GroupMe service, Microsoft One. Started with a semi-blind semi-blind SSRF primitive. And essentially I tried to access the localhost, but for some reason, doesn't matter what I did, everything was getting blocked. And then I will try to understand how can we discover more internal resources, what does the service or the feature actually does, in order to try and gain more with doing less. And another thing that was there, that there was a heavy rate limiting, essentially blocking me for trying to spam all the known payloads, and everything that I'm showing now is coming from a research and a lot of pain during the way. And these are like the takeaways from it. And along the way, I try to find all the interesting indicators in order to leverage the attack as much as possible. So I took the primitive and I tried to access the same primitive on a different scheme, and happily, this different scheme forced the proxy to expose a sensitive header that exposed an internal Kubernetes DNS record. And this DNS record pointed to the same primitive that was exposed from the outside, and I just took the primitive and I tried to figure out how can I use it just from internally, and like it was a simple Google search, or Bing, if you want to call it Bing. Bing search, like I wouldn't recommend on Bing, but like Google is also good. No, personal choice, I'm sorry. So documentation are your friend. Like always try to read the manual instead of just trying to fuzz. And once we had this set of primitive chained up, we managed to access an iframely resource from internal, which was the same primitive that was from the outside. And you're probably asking yourself, why do we even care? Because there was a specific API endpoint that obviously I cannot share most of the impact and the research here. You probably understand why. But that allowed me getting into sensitive Kubernetes API clusters by chaining the same primitive, and you can call it like double SSRF in a way, in order to bypass proxy rules that are applied externally that are obviously not implemented internally. And this allowed us access to something that was very sensitive. And this needs to teach us about taking a primitive that we already own and try to gain the most out of it. And the second one, it was a bit more challenging. It was another GroupMe. I think this was also maybe CVSS 9. Started with a blind SSRF. Like we couldn't really reach any assets and try to grab the content of it, but we did get some indication. And during along the way of the research, it was very tough to understand what are the internal endpoints and what we can do about it. And so I tried to spam with SSRF canaries, which you probably know, like CVEs and other components that are vulnerable within the network, as there is no authentication and no other things to defend. And all this time, I was like holding the answer, but I didn't know that this was the answer, and that's why I'm also presenting it here. So I did the same trick, tried to fool the API to give me their internal DNS record, which exposed a Kubernetes DNS record, and allowed me to essentially use the same primitive and access it twice in order to fetch an endpoint that you will see in a minute that was completely blocked from the outside. So you can see initially, I don't know if you can see my cursor. No. So initially on the attacker standpoint, the first point, we accessed one primitive from the outside with a /get, and we gave it a URL. This URL was the same primitive that is being served from internally, and we chained another one that goes to the attacker website or the sensitive API endpoint that we want to access. And the idea behind this is to try to less guess and less fuzzing and try to gain more like from what we have. And this taught me along the way about trust zones. So essentially, we could just take most of our findings and just compromise on the impact. But sometimes the security context changes everything. So we might be thinking that one trust zone is the same one as within, like the external one is the same one as within, but context changes everything. So it does also change the luck and the impact of our finding. So you can see in this request, I basically asked for the same endpoint, which is /pictures, just internally, and I validated this blind SSRF. So I couldn't access the endpoint, but what was interesting that when I tried to access an internal endpoint that wasn't exposed from the outside, I did manage to get a hit. So, and this basically allowed me to do all kind of other things that made this CVSS 9. But essentially, these API endpoints weren't secured, and they were being used by the same stance of externally as internally. And this perspective changes the way, or maybe our aspect that we look on SSRF. So I think that the main takeaway from this one, it will essentially bring in your primitive into its maximum impact by finding more about itself. So think about it, an application has so many layers and so many internal APIs that are not being exposed from the outside, and this essentially allows you to do something that is a bit different than the normal. Now, this is another case study, which I wouldn't say is product name or feature for different reasons. So we started with a simple SSRF primitive that essentially allowed me to access any website that I want just externally and fetch the content for me. Now, when I try to access the local host or other variations of loopback interfaces, everything was blocked. So I couldn't access any of that, and you can also see the response downstairs. And doing also a deep investigation of the primitive, it was very easy to just take this primitive and compromise on P3 or just try to fix it. But the idea behind the research was to show how we can take different indicators along the way and use them that are part of our design system. And in this case, there was a host header that essentially exposed, it was another proxy that essentially exposed the internal DNS record that allowed us to find the same primitive from the outside, just in the inside. And this gained us an internal access to a very sensitive API endpoint that wasn't exposed from the outside. And this is just one of many. There are so many different headers and responses that contain unique instrumentation and indication of things that happens from within, like proxy headers and other valuable components. It can be even in the content of the request. And using this approach, all our findings were elevated to at least P2, so minimum high. And it's also, I think, changed the way that MSRC and Microsoft think about mitigation right now. So every time that we're trying to deploy mitigation, we're just looking on it on the external side. But what happens if we take the same thing and assume that we're already compromised or already breached? What can we do about it? And this led us to a thing that says, like, by design doesn't mean that it's secure by design or secure by default. And this perspective essentially has offensive perspective and defensive perspective. So from the offensive side, try to look for self-reference potential. So there are many SSRF that we will simply track down and try to understand their potential by exploring out different sets of resources and environment variables that are not exposed from the outside. But no one actually checked the same primitive just from within. And once you transition in the security context, then it will be easier for you to understand what you can compromise, because it's very dependent on what the application actually promotes or delivers, right? Because if the application delivers just user to service functionality, that's one thing. But if it also implements service to service functionality, then there might be a service that uses the same API endpoint, but has a different security context and allows allows the primitive to run different different calls that are not allowed from the external. And one primitive can be enough. Like sometimes we will just try to spam and fuzz our way, and we always think about taking the big payload list and try to extract as good payloads or URLs from the same research that we have, and try to think more in squares and not in line. So take the same primitive and try to understand what you can do with it more, instead of trying to explore other components in the LAN. From the defensive perspective, try to think about trust zones more and when you propose mitigations. So mitigations nowadays mostly directed from the outside, and everyone focused on that. But trust levels has a significant meaning, especially after this research, because we found out that it wasn't, and I'm not speaking about 3 cases that I've just shown. We're talking about dozens of cases that have been generated using the same approach, just to different features. And we didn't also have a way to monitor these context switches. So even if someone exploited the functionality, we didn't have a way to monitor the second jump in the SSRF and even try to understand that it's a self-reference attack. And this is a key takeaway, that even Microsoft, with all the mitigation that we propose, it was hard for us to track it down. And the last thing is, don't assume that internal requests are safe. Internal requests can be doing anything possible, right? By accessing other internal resources, or by jumping into the same machine on different ports, but also consider the same application when evaluating it. So where does it lead us? Rethink about existing mitigations. Every IHTTP client implementation that is being implemented in some API needs to be evaluated and understand, what does this API endpoint expose to the outside, and what happens if we access the same API points from the inside. So when we're running a threat modeling, normally we will try to evaluate it from the outside, but we never think about it from the inside, because we don't assume that someone can access it from within, right? So try to think about, how can you take that and mitigate it before someone else exploits it. And it also exposes us to a new class of attacks. So basically, maybe now it exists in SSRF, but potentially it could be in all other different backclass. And it's something that we should consider as someone that defends on sensitive products or for just our own products. And the last thing that I will mention is that I don't think that there is nothing nowadays that can allow us to run context-aware monitoring, especially when the security context changes. And I think that it's just sometimes you don't need new vulnerabilities. You just need to think about the same one just twice. Thank you. And we're open to questions, so if anyone wants to ask anything, feel free.
Can I ask a question?
Yeah, sure.
Please go back to slide 30.
Yeah. Sure. $32? This one?
Sorry, maybe the next one. The one where you were showing diagrams. Oh yeah, this one. Thank you. So here, I have a couple of questions about that. First of all, was it really that safe that you nothing else was necessary.
Yeah. So you mean like what is the primitive here?
Yeah.
So the primitive essentially assume that you have one API endpoint that exposes you for an SSRF attack, right? And this SSRF attack essentially can be also triggered from the inside.
Okay.
So if I chain my SSRF, the first one, the initial one, which is the public one, to the internal one, I reach out from the internal API endpoint.
How does that happen? Because your endpoint would have to have an if statement if I'm being called from the outside to this, if I'm being called from inside, maybe add some authentication token.
So you mean how to defense around it?
No, how it was possible that it actually happened.
So imagine that you have an API endpoint that you serve publicly, right? And then this API endpoint is exposed through proxies, load balancers, etc., etc. But this API endpoint can be accessed from the same host, from within.
Yeah.
So if we access it from the outside, and the parameter that you're providing to the primitive from the external one is the inside one, you can access the internal API endpoint, if it makes sense.
Yes, but was there just an if statement somewhere in C# code that was like causing different behavior when called from outside and when called from inside?
No, there is no need to have any if, because think about it. When you go from the external stance, all your headers, like some headers are being stripped or being added, like your origin, host header, and other headers that indicate who you are. But when you are calling the same endpoint once again, these headers are forwarded to the next request. So then it means that it's coming from the service within and not from the outside. So think about it as a thing like they have no idea who runs this request, because in some cases the headers can come along the way even if you're running a few requests, but it really depends on the implementation. But at least from what we've seen, the headers are being stripped on the second one. And in some cases, sometimes headers are being ingested as like super global token admins or whatever that were added internally. So it's all about the play with the proxy and the other components that are being exposed externally. That's the whole play.
But then, so it must have been internal HTTP client that adding the header when the request was being sent from the local host. That's what happened.
Yeah, so imagine that you have like an IHTTP client handler, and on some endpoint that is implemented that accepts the URL parameter. It takes the URL parameter and it loads it into the IHTTP client handler. Now, this whatever /fetch endpoint still exposed and can be fetched from within. So it's going to be the same IHTTP client handler, just different headers, different indications about who called it.
Okay, but which building block actually decided that internally I'm adding this like super user header?
Because sometimes you assume, most of the time, people assume that the internal is trusted.
Okay, so there was if statement that was like, oh, I'm not seeing any export warranted for, therefore I'm a local, high privilege local host, and I can get it.
Yeah, in some cases, not everywhere, obviously, but it can happen more than it doesn't happen externally for a reason. But what I'm trying to say is that no one enforces those mitigations internally. They expect all the other external components to do the work for them and keep everything inside secured. Take a look at NAT. It's the same thing. We assume that the LAN is secured, so we have less authentication, less mitigations, and less things that are enforced from the outside, like firewall rules or proxy. Does it answer on your question? Yeah? Good question. So there is a tool we've developed that I obviously cannot disclose, but essentially picks all the host names and the internal DNS records from the responses and the request. You can either in Burp or Zap. We use Burp. But yeah, we didn't find it manually. Just the last one was being done manually, but the rest of them was being sent as alerts. So yeah, good question. You mean this one? Mm-hmm. So this is a very sensitive Microsoft feature of service that you probably all know, that essentially blocked in every way our way to access internal hostnames. But this header that was exposed by the proxy, because it has to know who to return the call to, was exposing the hostname, the internal DNS record, that ultimately wasn't mitigated when, like on the code level or also on the proxy level when trying to access it. So I used it from the externally. So from the external, I just used the primitive I had that you can also reach out. But this one was chained to the second SSRF that was pointing internally, which is this host, if it makes sense. Yeah? Any questions? If it doesn't relate to anything that was exposed during the research, I'm happy to talk about. Cool. Thank you very much.